Okay, before we get started today, I just wanted to say a few words about some of the discussion online regarding student conduct. And I can stand up here for an hour and talk to you about all the ways in which this is a wider problem in academia. But I'll focus on just saying a few words briefly and a bit more of a positive spin on it. So I think it's great that some of you have reflected on the fact that female and male professors and instructors and TAs are often treated differently. I think we all have unconscious biases, and the first step towards correcting for those is acknowledging that they exist, as well as discussing them. Okay, so thank you to the person who raised this on Discord. I think it's great that you've raised it as a point for discussion. My experience with students here has been very positive since I joined. No doubt that's in part due to the fact that I am a white male, so I have a certain amount of privilege that affords me respect that some of my colleagues, especially female colleagues, don't get. Like I say, the behavior towards me has been very good. I have heard about some of the things now that happened last semester, and also some of the treatment towards TAs. Now, by and large, the vast majority of you, your behavior has been exemplary. But there are some cases where people have, for example, been rude towards TAs in this particular class as well. So I would ask you to please reflect on that and also treat your TAs, your fellow students, other instructors with the same respect that you have afforded me. And that when it comes to your instructors and your TAs, we do make mistakes, but we do try our best. We are happy to correct those things if you tell us. So please do have patience. We are human. But to end again, on a positive note, like I say, I think for the vast majority of you, your conduct has been very good. I would say also remember that conduct extends to online spaces as well as in person, okay? So yeah, that's all I really wanted to say on that. And thank you again to the person who reflected this on Discord and raised it. Does anyone have any comments they would like to add at this point? No? Okay, let's do some math. Right. So today we're going to be talking about partial derivatives. So we did a review of derivatives on Wednesday. A little bit quiet, please, guys. Thanks. Okay, so we looked at derivatives on Wednesday, just to review them. Today we're going to be extending that to more than one dimension. Again, this is a common theme in this course, right? We're taking things that we know in one-dimensional context and extending them to more than one dimension. And show of hands who did the pre-lecture material. Great. Okay, so this should be hopefully straightforward. Partial derivatives are pretty straightforward. Okay, we know how to differentiate in one dimension. When we do it in two dimensions, say if we've got a function f of x and y, so we have here. If we want to take the partial with respect to x, we treat y as a constant and take our normal derivative with respect to x. If we want to take our partial with respect to y, which can either be written as this slightly curly d, df dy, or as f sub y of x and y, we take our derivative just as we would in one dimension with respect to y, and we treat our x as a constant. Okay, so that's the only thing we need to remember is the one or more than one variable if we've got a 3 or more dimensional function. Anything that we're not taking our derivative with respect to, we treat as if it was just a constant, okay? So there are some examples in the pre-lecture. I won't go through those in detail here. If we have a case like this, we've got a function, some physical or biological function here. We've got two variables, we've got pressure and temperature. We can take a partial derivative of our function here. So this is volume of 1 mole of an ideal gas. We can work out the partial derivatives with respect to t or with respect to p. And then we can think about what those actually mean. So in this case, if I take the derivative with respect to p, this is saying that the rate of change of volume is equal to minus 984 centimeters cubed per atmosphere. And if we take the derivative with respect to temperature, we get 16.4 centimeters cubed per Kelvin. Okay, so the units will differ because we're taking a different derivative. The P and the T here have different units, so that's why we end up with per atmosphere or per Kelvin. and it's telling you something about the rate of change in the final thing, in this case, volume, per unit change in temperature or per unit change in pressure, okay? We can take higher order partial derivatives as well. And in all of the cases you'll be looking at, it doesn't matter whether you take the partial, in this case, with respect to x, then y, or y then x. That's because everything that we're going to be looking at is continuous and behaves very nicely. It's not true in general. If you have things that are discontinuous, this isn't always true, but we're not going to be covering any of that stuff in this course. So as far as you're concerned for this course, it doesn't matter if you do f, differentiate f with respect to x, then y, or y then x, okay? Okay, so we can find our second, third, fourth, and so on partial order derivatives, and we just stack up the x's and y's in this case to indicate what we're differentiating with. And because the order doesn't matter, it doesn't matter if we have f sub xy or f sub yx, you end up with the same thing. Okay, this extends to more than two variables, like I said, and we can apply some of the ideas that we talked about on Wednesday in one dimension if we have a table of information to more than one dimension, okay? So if we have a table like this, we have wind chill index, and we want to know how is the wind chill index changing as the wind speed varies or as the temperature varies. We can do that by approximating our derivatives using the formulas that we had all the way up at the start. So just using these formulas, like we did the other day when we were trying to approximate a derivative in one dimension, we do exactly the same in two dimensions, either in this case by picking a point that's above, below, left or right, depending on whether we are going in the t direction or in the v direction here. Okay, so we can make those approximations here, and it can tell us something about the signs of this wind chill index. So in this case, as the temperature decreases, your wind chill should go up. So as you're moving in this direction, and as you have wind speed going up, your wind chill will also go up. Okay. We can also do this graphically. So we have previously estimated use level curves to estimate points, but we can use level curves to estimate the change in a particular variable. So what is our partial derivative, for example, at this point, sorry, this point here, as we move vertically or as we move horizontally. Okay, so you pick a point nearby and then use the formula for derivatives to approximate it. And that was all that was covered there. Okay, anything about any questions about partials before we go on to some problems? Nope, okay. Okay, this is just a reminder at the top because we'll be using this later on. These are our formulas for partials with respect to x and y. Let's start with an example of body mass index. Okay, so BMI is a function of both your height and your mass. So what I want you guys to do is calculate the partial derivatives of this function b, BMI, with respect to these two variables. So find the general derivative and then evaluate that derivative when m is 64 and h is 1.68 meters. And then interpret what that means, okay? Again, I'll go around and answer any questions next. You're working on that. Okay, let's see how you guys got on. Okay, so we want to work out our partial derivative. So in this case, it's going to be dB dm and dB dh. So in the first case, we're taking derivative with respect to mass. That means we treat this h squared as a constant, okay? So constant just comes out the front. So we have 1 over h squared. We take the derivative of m with respect to m. So we have 1. So this times by 1, which is 1 over h squared. If we do our partial with respect to h, now our m is a constant, and so we're taking the derivative of 1 over h squared. Note that we can write this as mh to the minus 2. So we just use our power law as we would normally. So the minus 2 comes out the front. We have minus 2m over h cubed. Again, if that's not quite clear, we have minus 2m h to the minus 3. This is because this power comes out the front, and then we reduce it by 1. Okay, so those are our two general formula, and then we want to substitute in our values for this particular person when M is 64 and H is 1.68. So the notation for this, you do the straight vertical line next to it, and then you can put your values there. So M is 64 and H is 1.68. So there isn't actually an M here, so that doesn't matter. So we just have 1.68 squared, which is somewhere around 0.35. 0.35 what? Using math. Okay. So what have we got to start with here? So BMI on its own, we have mass, which is measured in kilograms, and height, which is measured in meters, but we have height squared. So this is kilograms per meter squared is our unit for BMI. And we've just taken our derivative with respect to mass. So this is going to be our units for BMI, kilogram per meter squared per kilogram. Okay, let's do this for dBdH. So we need to evaluate this. When M is 64 and H is 1.68. In this case, you're going to have -2 times by 64 over 1.68 cubed, which is somewhere around -27 kilograms per meter squared per. Anyone? Per meter. Okay, so it's per meter because we're just taking derivative with respect to H measured in meters. Okay, so -27 kilograms per meter squared per meter. We don't usually think about people's height changing in units of meters. This is our standard unit, but we can think about this in terms of centimeters instead. So you could write this as per centimeter increase. So for example, I could write this, I could change the units if I wanted to and say this changes as 0.27 kilograms per meter squared per centimeter, for example. So what is the interpretation of these things? Let's go back to the mass one to start with. So this is saying, because this is a 0.35 kilogram per meter squared per kilogram change, that's saying that our BMI changes for each 1 kilogram increase in mass. We have BMI increasing by 0.35 kilograms per meter squared. Okay, so that would be my interpretation of what's going on here. Every kilogram of mass you add, BMI goes up by 0.35 kilograms per meter squared. Note that because this doesn't depend on mass, it doesn't matter what your starting mass is. Okay, this is the same regardless of what your starting mass is. On the right-hand side, we can say that each 1 centimeter increase in height causes a decrease in BMI of 0.27 kilograms per meter squared. Note here, crucially, we're talking about at a particular point. So just to clarify what I said a moment ago, the general function for dBdM has no M in it. So that means no matter what my starting mass is, my BMI is always going to be increasing by 0.35 kilograms per meter squared for any starting mass. For our height, because this is a function of M, what I'm saying down here, each 1 centimeter increase in height causes a decrease in BMI of 0.27 kilograms per meter squared, only applies at this particular mass and height. okay? So remember, whenever we're taking our derivatives, what we're thinking about in one dimension, you're drawing a tangent to that curve in one dimension. We're doing something analogous here. We're talking about tangent planes, which we'll talk about on Monday. So this thing on the left is true in general because there's no m in my PBDM. The thing on the right, what I've said there, is only true at this particular point, okay? Because there's an m and an h in this function. Let's move on to another example. So here we've got a table. Remember I said when I was summarizing the pre-lecture material, that if we've got a table of values, just like when we're looking at one-dimensional things, we can use these to approximate partial derivatives. So here we've got temperature humidity index. So we've got humidity in H going along the top and temperature in Fahrenheit. You guys know how I feel about Fahrenheit. So what you want to do here is you want to work out your temperature humidity index I. So I is a function of both temperature, T in stupid units, and H in percentage. And you want to approximate your derivatives, your partial derivatives, at a particular point. So at 90-40, so that's when temperature is 90 degrees stupid units and 40% humidity. So that's this point here. And you want to approximate your partials. So you want to approximate the partial in this direction and in this direction. In fact, it's not quite correct. I'm going to do it in this direction. The reason being that T is increasing going down. Obviously, the signs will flip around, but you're usually best to orient yourself as a variable is increasing. That will help you make sure that you don't get your signs the wrong way around, okay? So think about things as your variable increasing in both cases. Work out your partial derivatives by choosing a nearby point and using your formula that we had at the start. So that's these formulas here to approximate. So remember we did this in one dimension. We're doing exactly the same here, but now we've got our partial derivatives, okay? Again, I'll walk around and answer any questions you guys might have. Fair enough. I'm not going to be that offended. But... Okay. Okay, guys, let's see how you got on. So I'm going to switch my colors around just for consistency. Okay. So we're going to do dFdt first of all. Okay, so T is varying in the vertical direction. So I could either pick this point here or this point here. It doesn't matter which one I pick because I'm making an approximation. If you think about what's going on, you've got, I'm just going to draw a slice through this, okay? So think about whenever we're doing our partial derivatives, regardless of whether it's a continuous function or whether it's from a table like this, we're essentially treating one thing as constant, and then we're taking a slice through it. So if you imagine you had like a surface of a surface that looked like a bell, if you took slices through it, you'll have a curve, okay? And depending on where you take that slice, you'll have a different curve, okay? That's kind of what we're doing here when we're doing our partials. When we've got something that's discontinuous like this, the points that we have here will look something like this, say 86, 93, and 101. So they might look like this. So if I want to work out my gradient here, this isn't a nice smooth thing. It's not like it varies like this, okay? So if it was continuous, I'd be able to just, pick that point and work out my gradient. We can't do that. If I choose the point below, then essentially I'm working out this gradient here. And if I choose the point above, I'm working out this gradient here. In general, those two things are not going to match, right? But at the end of the day, all we're doing here is we're approximating it, okay? So you might get a different answer if you picked a different point to me. As long as you are consistent, though, with what you've done, then that's fine. Okay, so I'm going to pick this point 101 here. So how do we work out this partial? We need to work out the difference between what's going on for our function. So f at 95, 40, so 95, 40 because of this, minus our f at 90, 40 all over the difference in our t's. So this is 95 minus 40 minus 90. There we go. Okay, so someone asked if the order of these things matters. It doesn't. I could have switched these around. As long as I switch these around at the bottom as well, the signs will stay the same. Okay, so the order in which you do it doesn't matter. Conventionally, we tend to do the bigger one minus the smaller one in terms of how your variable is moving. Okay, so we work this out. So we have 101 minus 93 over 5. So this is 1.6 degrees Fahrenheit perceived temperature per degree Fahrenheit actual temperature. So remember that this is the temperature humidity index is the perceived air temperature. And what we're doing down here is we're varying the actual temperature given humidity. So what this is saying is at this particular point, when you've got 90 degrees Fahrenheit with 40% humidity, every 1.6 degree increase, 1.6 degree Fahrenheit increase, blah, blah, blah. Let's turn it around the other way. Every 1 degree Fahrenheit increase in actual temperature yields a 1.6 degree Fahrenheit increase in perceived temperature. That was a very wordy response. Okay, let's go in the other direction. So now we want to work out the change at this point with respect to humidity. So I'm going to choose this point here. Again, you could have chosen this point here. Would have given you a different result. Here we're going to do F at 90, 50, 50 because of this 50 up here, minus F at 90, 40. And we're going to do 50 minus 40 on the bottom. So that's 96 minus 93 over 10, which is 0.3 degrees Fahrenheit perceived temperature per percentage change in relative humidity. I'm just running out of space there. It's relative humidity. Okay, so what's that saying? That's saying that for every 1% increase in relative humidity at this particular point, so when the actual temperature is 90 degrees Fahrenheit, the relative humidity is 40%. For every 1% increase at that point in relative humidity, we get a 0.3 degrees Fahrenheit increase in perceived actual temperature. So the actual temperature is not changing, but the perceived temperature is changing. Okay, so remember that these things only apply at this point. So as soon as we start moving away from that, that no longer applies. So that wouldn't be the case, say, if we wanted to work out the the effect of relative humidity on temperature up here. Likewise, if we wanted to work out the change in relative humidity as we vary temperature down here. Okay, so just like as you work out your gradient against a curve, that only applies at that particular point. So you might have a general expression for the gradient, but when you substitute in values, which is essentially what we're doing in here, you're only working out the gradient at a particular point. It's the same thing here, okay? It's not true in general, it varies. Okay, so these descriptions of what's going on only apply to that particular point that I've chosen, 90, 40. Okay. Thing about infectious diseases. How many more questions have we got? Okay. So a very simple model for the spread of SARS. So in this case, let's put it SARS-CoV-1 rather than SARS-CoV-2. We have R0. R0's used extensively in epidemiology. This is the average number of infections that each infected individual produces in an otherwise susceptible population, which is a very wordy definition. Who's heard of R0 before? Okay, a few of you. This is one of those really fundamental things that falls out of even the simplest models, but tells you something quite powerful. You can derive things like vaccination thresholds from this, even very simple models. It can tell you the problems of rolling out vaccines slowly for things like rubella, because you end up with, if you don't vaccinate enough individuals quickly, you can make things worse. That's because you increase the average age of infection, all of these things link back to R naught. Here we've got V as being the fraction of the population that is vaccinated. D is the average number of days an individual remains in the population while infectious. So you can think of D, if we're able to reduce D, that's some measure of maybe quarantining and testing people. And then they go into lockdown themselves or self-isolate. V is going to be just proportion vaccinated. And so we're going to suppose that an outbreak just began. So this means that pretty much everyone in the population is susceptible. And individuals stay infectious for 4 days and no one's vaccinated. So we want to evaluate what is our R naught at this point, and how is our R naught changing if we were to start vaccinating dR naught dV, or if we were to somehow change how long they were infectious for. Okay, and then do this at this particular point here when D is equal to 4 and V is 0, and then think about a biological interpretation of those results. Okay, have a go at that. Okay, guys, there's a little bit of confusion, I think, as I was going around. Some of you made some progress, some of you didn't know what to do, I think. So let's work through it. Okay, so the first thing we need to do is just evaluate R naught when D is 4 and V is 0. So that's just substituting in these values. 4, 0. We're going to have 5 times by 1 minus 0 times by 4 over 1 plus 4. Which is just 4. So what does that mean? That means that we're getting, early on in this outbreak, 4 new infections per infected individual on average. So during the early stages of an outbreak, R naught tells you something about how quickly that's taking off. You'll probably be familiar with seeing exponential growth during the early stages of COVID. It's very difficult to estimate this in real time, and often there might be delays to it. So you kind of maybe only know what happened 2 weeks prior because you have incomplete data in reality. In models, we have perfect data and assumptions about what's going on in the mechanisms here. So yeah, the R naught is really crucial, like I said at the start, for determining ideas about control in particular. So how do we respond to infectious diseases? Things that have a high R naught are typically much harder to control. There's actually a really cool finding, just as an aside. If we want to work out our vaccination threshold versus R naught, it looks something like this. If I'm going to call this VC, VC is, in the simplest models, 1 minus 1 over R naught. Okay, so this is why it's so important to look at R naught. It tells us something really important. So when COVID came into the human population, I mean, estimates vary because it's population dependent, but it's kind of down here, somewhere, say, 2 to 4-ish, depending on population. That gives quite a wide range for what your vaccination threshold would be. We're talking anywhere potentially from 50% up to 75%. Measles is somewhere all the way over here. So the R naught can actually vary. It's not a very good diagram of it. It can actually vary somewhere between 12 and 18, I think, is most of the estimates for measles. That kind of means you need to vaccinate something like 93 to 95% of the population, which is why it's super difficult to control measles. Okay, so that's why we care about R naught. It tells us something about control. This is a super simple model of what R naught looks like. But it tells us here that to start an outbreak, we're getting 4 new infections per infected individual for this particular disease. Okay, the next thing we wanted to work out is the partial derivatives. So let's do those. So dR naught dd. So I don't have the expression here, but we have 5 times by 1 minus b. So we're treating our b as a constant, the 5 as a constant, so that just stays the same at the front. We have a d over 1 plus d, so we need to use the quotient rule here. If we use the quotient rule, we're going to have 1 plus d minus d over 1 plus d all squared. This d here cancels with this minus d. So we're going to have 5 times by 1 minus b over 1 plus d all squared. We're asked to evaluate this when d is 4 and v is 0. So just substituting those values. 5 times by 1 minus 0 over 1 plus 4 squared. So we're going to have 25 on the bottom, 5 on the top. This will be 1 over 5. And the units here, remember our R naught is our new infections per infected individual. So I'm going to abbreviate that. New infections per infected individual. And then because we're taking our derivative with respect to D, and D is measured in days. So this is days whilst individuals are infectious in the population. So this is a very wordy response. So this is for each unit increase in D, so that's for each additional day an individual spends infectious in the population, they are going to create on average 1/5 of a new infection. So 1 in 5 new infections. So this is per day in population while infectious. So what does this mean? What's the interpretation here? This is saying that if we can start quarantining individuals, because this is positive, we're going to be reducing R naught. So if we can reduce D, we will reduce R naught. If we increase D, we will increase R naught. Okay, so it tells us something about the strength of our control and what we can do. Let's do this with respect to V, dr naught dV. In this case, our D is going to be constant and our V is going to be our variable that we're taking derivative with. We've got a minus V in here, so we're going to have a minus coming out the front. There's no powers on V, so that's just going to get dropped. So we're going to have minus 5 times by our D over 1 plus D. So remember the D's are just being treated like constants here. Again, we can evaluate this. D is 4 and V is 0. So V doesn't actually appear in here at all. We have minus 5 times by 4 over 1 plus 4, which is minus 4. Again, units of R naught, so new infections per infected individual. And we're doing this per proportion vaccinated. So again, you might, as with the BMI example, you might want to change the units here. So rather than proportion vaccinated is just going to be going from 0 to 1. So you might want to say per 10% of the population vaccinated, this goes down by 0.4. Okay, so we can rescale it according to something that is maybe easier to work with, because sometimes the units are not very helpful to work with. Okay, so this is a biological interpretation. So what's the key takeaway here then? Like, quarantining is good. I mean, all else being equal, if 1 unit of quarantining was as good as 1 unit of vaccination, or as costly, then vaccination would be better. Okay, so vaccination is more restrictive, better than quarantine, essentially. I'm not going to go through this example here, but this is very similar to what we did with the table. A couple of quick announcements, 30 seconds, then you can go. Office hours next. If you can attend office hours rather than coming to me at the end, that would be helpful. Midterm next Friday. I will share a formula sheet hopefully later today for that midterm, for what you need to know. And I will review the midterm, give some help on what we've gone through next Wednesday, okay? See you next week.